Hello everyone, and welcome back to what I believe is the final session of the NZRSE Day 1 program. So we've got two speakers in this session, and the first one is Chris Scott. Chris leads our research software engineers. We're a computational science team here at NZRSE. He's been around at NZRSE for quite a few years now. I should have checked the exact number of years, Chris. Sorry, but many, I think it's fair to say, and has worked with quite a few of you over the years. So great to have Chris here in the program. He is going to be presenting on developing a Julia interface to the DACE C++ library. Over to you, Chris.
Thanks, George. Yes, I'm Chris, a research software engineer at NZRSE, and I'm going to talk about creating the Julia interface to DACE. This is work I've been doing with Jack Yandley, Adam Evans, and Roberto Amelin at the University of Auckland, and Alberto Fossa at the University of Texas. So I'll give a bit of background and motivation first for why we wanted to do this, and then I'll probably explain a bit about a couple of different options we looked into for creating the interface. I'll give some implementation details. And it's worth saying that this project is still in progress, really. It's not complete, so we're still working on the interface. Although we do have something that's usable now, it's still going to get developed further. But I guess the idea here is that maybe some of the tools we used or some of the things we found as we were developing the interface could be useful to others if you're in a similar situation. So first to say, we have the NZRSE consultancy service, which has already been mentioned, I think, by Alex earlier this morning. And this service is how my time was contributed to this project. We had a consultancy project. With the NZRSE consultancy service, we can work on a really wide range of problems, and someone from the NZRSE team gets basically assigned to work within a research group and lift the computational capability. And as we heard from Alex earlier, in that project, he was looking at fixing a memory leak in a scientific software. I think what we'll hear from Maxime next is where he used a large language model in weather forecasting, and that was also started off as an NZRSE consultancy project. And here we're talking about creating a Julia interface to some C codes. There's a really broad range of different problems we get involved in. And we're really interested to hear if anyone has some interest in talking to us about finding out more about this service. Please get in touch. Just to say a bit about the astrodynamics research group at University of Auckland as well. So this group, they're interested in developing solutions for spacecraft guidance and space situational awareness. Both of these problems require understanding of uncertainty propagation in dynamical systems and how to control their evolution. In order to solve these problems in an efficient manner, they use high-order Taylor expansions. And this is where the DACE library comes in. DACE is the differential algebra computational toolbox. And this library enables automatic computation of high-order Taylor expansions. And we've got a couple of examples here of work that's been done using DACE, the DACE library. I think this is probably the C++ version. So on the left, we've got spacecraft guidance for a docking maneuver with initial uncertainties. So you can see some initial uncertainties in the red box, and then the set of trajectories that the DACE algorithm that the guidance algorithm was able to come up with to reach the final point. On the right-hand side, we have probability density function propagation in orbital dynamics problem. Okay, so some motivation for why we actually wanted to create the Julia interface. So the DACE C++ library, there's a feeling that it had quite a high barrier to entry. Say, for example, if you have a new PhD student coming through and starting, maybe they haven't learned about C++ and compiled languages in their earlier studies. So they have to spend quite a lot of time getting familiar with build systems, compiling code, linking libraries. They need to then learn how to write C++ code, which might not be the easiest. And also, it takes quite a lot of expertise to be able to, if they need to add some new functionality to the C++ code, to actually come in there and do that. There's a lot of understanding required. But the research group had some expertise in Julia and had some previous experience using Julia. And there was a feeling that it's easier to pick up and get familiar with using Julia. Julia is a developing language. There's a large community of people writing libraries for Julia now, which means you don't have to do everything yourself. You can build on top of what other people have done. There's no need to compile code yourself, and it's easier to write performant code in Julia compared to some other languages that are also easy to get started in, like maybe Python or similar languages. So the decision was made that we want to try and make a Julia interface to hopefully make it easier for people to come in and start using the DACE library and all the features that it provides. So first, I'm going to look at a couple of different options for how we could interface from Julia to this C++ library. And the first option is called ccall. This is built-in Julia functionality, which allows you to call C and Fortran functions from Julia. You just need to have your C or Fortran or C++ code compiled as a shared library, and you can then call functions within that using ccall. So with this approach, the interface would be written entirely in Julia. There would be no changes required to the C++ code, but we would have to replicate the entire C++ interface in Julia. And what this means is, so the core of DACE is actually written in C. So there are a bunch of C routines that the C++ interface is built on top of. So when you create a class in C++ and you have methods in your class, those methods are calling the underlying C code and passing structures around to the C code. And we would have to replicate that in Julia. And so on these next couple of slides, I've just got some examples of a little bit of code. I mean, the basic idea here is to kind of show you how much work is involved in creating the interface in this manner. So on the left-hand side here, we have the DA class in C++. And this is sort of the fundamental data type in DACE, which represents a polynomial. And most of it's cut out, but we can see that there is one type here. I'm assuming you can see my cursor. I'm not sure, but I think so. We can see that there's this one attribute, DACE DA, called mindex here, which is sort of the fundamental type that gets passed around to all the underlying C routines. And so in order to be able to create the Julia interface, we need to understand a bit more about this type. So we have to dig into the C code, and we see that the DACE DA is a variable, which is a struct, and has a couple of unsigned integers and another struct, which is just a couple of numbers. And so in order to create the Julia interface, we actually have to replicate these structures in the Julia code before we can actually call the underlying C program. So here we can see in Julia, we create a struct, which is equivalent to the struct, the monomial struct in C++. Then we have the variable, which builds on top of that, which is equivalent to the variable in C++. And then equivalent to so in C++, we have the class DA. In Julia, we would have a mutable struct DA, which has the same, an equivalent member attribute. Index is equivalent to the mindex there. Same, the types are equivalent. And the reason we use a mutable struct in Julia is because when we create the struct, we have to allocate some memory in the C routines, and the mutable struct allows us to attach a finalizer, so that when the DA object gets garbage collected in Julia, we'll be able to call the C routines to free the memory that was allocated in C. And just quickly looking at how we actually create the DA object. So in C++, we have a constructor, which is just the default constructor, which creates an empty DA object. And in this constructor, we've got a call into the underlying C, the C core of DACE, which is to this function called DACE allocate DA. And it just takes two arguments. One is the mindex variable that we saw in the previous slide. And then we're also passing in 0 as well. And we have a destructor as well, which calls DACE free DA and passes in the mindex again to free the memory when it gets destroyed. And to create the Julia interface using this call approach, we have to replicate this functionality in Julia. So we might have something that looks like this, where we have a function DA, which is the constructor for the mutable struct we saw on the last slide. We have the equivalent mindex variable, and then we're using ccall to call the DACE allocate DA function, exactly the same as we saw in C++, but we're calling it from Julia. libDACE is just the shared library that contains the DACE code. We have to pass in, the return types and the argument types and the values of the arguments to pass to that function. And you can also see further down that we have the finalizer, which we'll call DACE free DA, the same way that was happening in C++. But what you can see from this is that there's quite a lot of work involved, even though the interface is written in Julia. The interface is written in Julia with this approach. You do actually have to understand the underlying C and C++ code to be able to mimic the interface in Julia. So the second option we looked into was using a package called cxxwrap.jl. So this is actually a third-party library, so it's not part of core Julia functionality. So we are adding an extra dependency, but but I think, it looks like it's actively developed, so I think there's probably low risk that it's going to go away. In this case, the main difference is that the interface is mostly defined in C++, but you can extend it in Julia. So you don't have to write C++ code if you want to add more functionality later. You can do that in Julia too. And here's an example of how we would create the interface using this approach. So this is C++ code in the top box, where we're adding the DA object, the fundamental type from DACE that represents a polynomial. And we're using this add type method. So we're saying we want to add a type into the Julia module. The type should be the DA, the C++ DA class. And in Julia, we want to call it DA as well. And the second argument here is actually just saying that we want this, when we create this type in Julia, we want it to the base class to be a real number. And then on the second line here, we just say dot constructor, and we're creating the default constructor that takes no arguments. And so this second line here is really equivalent to the whole of the last slide, where we had to have that big block of Julia code. So it's much less code required actually to create the interface in this way. And we can easily add in the other constructors. So we have a couple of different constructors for creating the DA objects in C++. So we can move those across to Julia as well. And if we want to add functionality, so for adding a method like DA get coefficient, it's just a single line here where we can add that using CXXWrap. Whereas with the CCall approach, we'd have had to add in like the whole block of code that makes the call to the underlying C library, and it would have been a lot more involved. And so with CXXWrap, this is the part of the Julia code that actually loads in the C++ library. So here we're just using CXXWrap, and we use wrap module functionality from CXXWrap, which just points to the shared library where we compile the C++ code, and it tells it which function within that shared library is defining the interface. And you can then, if you wanted to, after doing this, you can then add in more functionality on the Julia side. So in the end, we decided to go with the CXXWrap approach just because it was so much faster to implement the interface using that approach. We had to do much less coding, and then although you have to modify the C++ code, you'd have to spend time understanding the C++ code whichever way you go. So we thought it was a good approach to take. And there's actually a more detailed comparison on this link here if you're interested. Okay, so now to just talk about the implementation. So in terms of structure, we have the DACE C++ library, which we've extended using CXXWrap, and exported the function to Julia, and that lives in this Git repository. Once we have created that library, we need to build it into a shared library which can be loaded from Julia. And the standard approach to doing this in Julia is with these so-called JLL packages. So we use a tool called binarybuilder.jl, and inside binarybuilder we have a recipe file or a script which has like a CMake command to build our library, and binarybuilder will like cross-compile our library across all the different platforms like operating systems and versions of Julia that we support, and it will then it will archive those binaries, and then it will create a Julia package called dace_jll.jl, which we can then load later on. And so the final piece is the dace.jl Julia package, which lives in its own Git repository. And this Julia package has a dependency on the JLL from the previous step, so that we can load in the appropriate shared libraries for whatever operating system the person's running on. And then we initialize the interface using cxxwrap.jl. So the goals we had with this project were we want to have the same functionality as the C++ interface. So to do this, we go through and export all the types that we want, such as the DA, which is the basic type for a polynomial, algebraic vector, which is it's just like a vector, but it has extra differential algebra functionality on top of it, and make these available in Julia. We also want to have compatibility with other Julia packages, such as differentialequations.jl, because this means that we can, say, for example, use solvers from those packages instead of having to write our own. So it really helps if we can have compatibility with those libraries. And we were able to do this by choosing appropriate base classes for the types that we're exporting. So, for example, the DA type should have a base class of a real number, and the algebraic vector should have abstract vector type. And for example, for the DA type, we need to implement all the comparison operators and other operators so that differential equations, so that they can be used with differential equations. I just wanted to mention something about documentation, because we wanted to make sure we had good documentation of the interface, but it took us a while to figure out how to do that. So let's say, for example, here we have a method da set EPS that we want to export to Julia. We can use the mod.method command that I showed earlier as well. And the first argument is just the name that the method will have in Julia. Second, we have a lambda function that shows how the function works, so what arguments it should take, a single number, and what should happen in the function and what it should return. And then the third argument is a doc string. Now, if we leave it there and just use that, when Julia generates the documentation, we just see this string that's written here. That there are no, it doesn't automatically add in a function signature. So we would have had to manually go through and add all the function signatures ourselves, which would have been quite difficult to maintain and it would have taken a lot of time. So we really didn't want to do that. And in the end, we ended up finding this docstring extensions.jl package, which we were able to set up to automatically add the function signatures in the Julia docs, which we found that really useful. So we ended up with something looking like this, where we have the set EPS signature at the top. And even for a simple function like this, you can see that although we've said we just want to take in a single double, so it's a double precision, when CXXWrap creates the interface, it actually lets you take in a double or an integer or an irrational constant. So if we'd had to go through and manually add all of those, it would have been a lot of work. So it was really useful that we found this docstring extensions package. Okay, so just quickly mention about validation. So in order to validate that things are working correctly, we looked back at when the DACE C++ library was originally developed, I think during a European Space Agency project, and they had a fairly rigorous document showing what validation tests need to be run in order for the project to be successful. And so we went back and started to implement some of the validation tests from that document. And so an example is on the right-hand side, where we just have a test that says that the sign function in DACE is working correctly. And what's happening here is, on the first step, I think here k could be 10, maybe, in these tests. And so here we're initializing DACE for 10th order calculations with one variable. Then we create x, which would be a DA, so it's a polynomial representing x. And then f would be a Taylor expansion representing sine of x. And so for simple functions like sine and exponential and so on, we know what the coefficients of the Taylor expansion should be. So then later on, we're just checking that the coefficients from the DACE Taylor expansion are matching what we know they should be. And then in this way, we can verify that the basic functionality of DACE is correct in Julia, as well as in the C++ original code. And the second type of testing that we did also, we could set up some simple tests where we run the same thing using the C++ version of DACE, the Julia version of DACE. And we also compared to other Julia libraries that do similar things like TaylorSeries.jl. And we were able to show that solving the same problem in the same way with the different approaches also gives the same result. Okay, so just a quick summary. So we now have the initial implementation of DACE.jl. The basic types and methods are available in Julia. We have compatibility with differential equations.jl. And we've actually released an early version of this package to the general registry, so it's really easy to install DACE now. We haven't spent a lot of time looking at performance yet. There were some early indications from some very simple tests that we might be a bit slower than C++, but we look like we're performing well compared to other Julia alternative packages. But that could be something we want to revisit in the future once things are more stable and pay a bit more attention to performance. And the next steps really are to start using DACE in the research, so that we at the moment we've just been testing it, but now we might actually start to use it in anger. And when we do that, we're probably going to come across more problems and missing functionality that we'll need to start adding into DACE. Yeah, but that's all from me. Happy to take questions.
Awesome, thanks, Chris. There is a question in here from our friend Alex. I'll read it out for everyone's benefit. Oh, there's more coming in. In the CXXWrap approach, you showed multiple constructors, each templated, but none taking any arguments. Does Julia support templating? How do you map the constructor on the Julia side to the correct constructor on the C++ side?
Yeah, so I'm not sure if I can go back. I'm not sharing now, but that doesn't matter. I think when you create the constructors with CXXWrap, you actually pass in the arguments to the constructor as template parameters. So inside the angle brackets is the constructor arguments. So I created one constructor that had no arguments, one that had a single double, and one that took in a double and an integer. So that's how you pass. That's how you tell Julia that you want to create the different constructors for the object. I don't think Julia supports templating, but I don't know. Yeah, that I don't know if that helps, Alex, but we can go back and I can show you a demo probably if we can go back to the slides another time.
Okay, cool. And we'll sneak one more question in from Wolfgang. How well can Julia and C++ integrate when it comes to memory management? For example, around ownership of memory allocations. Is the programmer expected to fully manage this, or is there some way to leverage something like C++ smart pointers and or move semantics?
Yeah, good question. So in this case, so I'm not an experienced Julia developer, so I can only say what we did in this project. And in this case, because we have the memory is managed by the C code, so we call some routines, and that memory is then allocated in C, and it needs to be freed in C as well. So we just have to keep track of that memory. With the C call approach, you have to keep track of that memory and deallocate it yourself. With the CXX wrap approach, it's all done implicitly. When you call the constructor, it automatically adds in a finalizer, which will clear up the memory as well. So I think in this case, we didn't need to pay too much attention to memory management. I'm not too sure what you could do with smart pointers. I haven't looked into it.
Awesome. Thanks, Chris.
Thanks.
Right. Now on to our next speaker, and he happens to be the last speaker of the day. So hang in there, folks. This is Maxime Rio. He is a data scientist at NIWA, and he is presenting on self-hosted LLMs, a weather forecast LLM case study.
Oops. Tēnā koutou katoa, ko Maxime Rio. How? It's great pleasure today to talk a bit about this self-hosted LLM experiment, and this work has been done in collaboration with Tristan Meyers and Chris Brandolino, who are meteorologists at NIWA. I'll start with just very few words about myself. I work as a data scientist at NIWA. I love developing machine learning models, in particular probabilistic ones, optimize Python code and workflows, and test and deploy all sorts of tools on the HPC, but most importantly, doing this for others, for scientists. I've been doing this for now more than 10 years. I love it, and I do recommend if you're considering this type of career. And on my spare time, I do other things, as you can see on the right. And if you're wondering what it is, these are profit roll, and they're very, very good. I want also to mention, as Chris said before, that this project originated as a consultancy with NZRSE, with the Computational Science Consultancy Service, which Chris and Alex are part of. They do all sorts of amazing stuff, from code optimization to workflow prioritization. They do things on the HPC, but also outside of the HPC. I do recommend to work with them. If you want to know more, don't hesitate to contact them at support@nzrse.org.nz. On this note, let's talk a bit about LLMs. I won't do an in-depth introduction. I'll just throw some generic information at it, about it, in case you don't know about it. So these are very deep neural networks. Some of the latest instantiations of the Llama 3.1 model, for example, have more than 400 billion parameters, quite large. They are trained on very large data sets, like the PAL, which is a set of publicly available text data, almost a terabyte of data. To train them, you may need a very large machine. Again, looking at some information from NVIDIA about the Llama 3.1 trained by Meta, they use 16,000 H100 GPUs. And then for obvious reasons, the training, and we'll be talking mostly about inference today, but the training of these models is done by large companies or large institutions. And if you're interested into the details of how that works, under the hood, it's called a transformer architecture. I won't go into the details today, but you can see a graphical depiction of this on the right. They originate mostly from text tasks, so like doing text completion. And you can do more advanced things like document summarization. And one usage that makes them very popular are the chatbot, like what you can do with ChatGPT for question answering. And in that context, came the idea that we were like, hey, we'd like to do a few things with LLM, and what about we try to generate some text forecasts? So we take the numerical weather prediction model, or NWP models forecasts, so numbers, and we try to turn this into a text that customers or people can read. And that will be actually a very nice pilot project for a couple of reasons. First, it will expose our forecasters to this new technology so they can try it, and we can learn from our side the pros and the cons of what is it good for, what is it bad at, and from the software engineering point of view, also what are the things you need to consider when you want to deploy such systems. And on the right, you have sort of the summary of what we want to achieve. Like data comes in, we transform it into text, we have a prompt, so a request for the LLM, so do something with that data, and hopefully it sends out a credible forecast. The end product, kind of, so what we are not playing with the forecaster is a dashboard. One more today, but this one has been done with my very hands, and I'm not a designer, so it's only throwing a lot of knobs on a web interface and making sure that we can play with all the little parameters of the model. So on the left-hand side, you'll have many fields, so how we can sub-select the information from the model that we want to inject, from the numerical weather model that we want to inject into the prompt. And on the right is more like, okay, what is a kind of a template of what we want to request to the model, and we will kind of merge the two, send that to an LLM when we press the generate forecast button, and ta-da, we have on the left we'll have whatever the LLM wanted to generate for us. We hope it's good. And on the right, we'll have additional diagnostics. This is where it's interesting to do a bespoke development, so to really make this software for the actual task at hand and not a generic chatbot. Because here we can have all the diagnostic of, okay, what was the exact forecast for that location at that time? Does it match the text which has been issued? And we can also add more tabs. That's what we did here, to look under the curtain a little bit to see, okay, how much time does it take to do the prediction? What are the sort of the token generation speed and all sort of things. So now I'll detail a little bit about the architecture of the software architecture of this project. Just one word of jargon that's good to know. What we're trying to achieve here is called a retrieval augmented generation, which means that we are gathering some data, we're merging it with a prompt, a text prompt, and we feed it to an LLM. And so all of this is driven by a Python script, which has a dashboard relying on Streamlit Python package. That one will be the web interface, which is with which the user will interact. But then once all the setting has been set, what happens is we'll go to the data retrieval. So we are accessing a couple of servers that unfortunately the same computer can have access to, and to retrieve the numerical data from the forecast and also the observations from the database. We format that, so we convert it into text, and we merge it with the prompt of the user, send it to an LLM. So the LLM I'll get in an instance of what we're working with, but it's sitting in a Slurm job on the HPC. And all of these interactions are mediated by simple HTTP requests. We do a bit of recording of our experiments, and we display it back to the user. Okay, so as the title mentioned, this is a self-hosted LLM experiment, and the question that could arise is, okay, why go that way? A couple of reasons. One, we have the chance to have access to some shiny GPUs on the NZRSE platform and the new HPC platform too, so have access to A100. And also, it's a good time to try open source equivalents of LLMs, because some have a performance equivalent to ChatGPT 3.5, which for what you're trying to do and what we're trying to do, maybe it's enough. We don't need ChatGPT 4. And also it's improving every day. It's hard to keep up. One thing which was a particular concern of mine was I was a bit nervous of leaking internal data to a third-party service without knowing exactly what are, the little fine footprints about what they will do with our data. So at least I know I'm on the safe side if I keep everything on our infrastructure or on the national infrastructure too. And also, if you deploy your own LLM too, you can play a bit more with fine control of the LLM parameters of the software parameters. And for future, if we want to go that way, we can also fine tune the LLM, so retrain just partially the LLM. In terms of software technologies, what we've used are two things mainly here for the LLM part. So first, we rely on this very nice llama.cpp open source inference engine, and that's so as the name says it's a C, C++ runtime. It can run on a CPU or a GPU. And once you run it with the weights of your model, it will expose a simple server that you can access with HTTP request. And it even has an OpenAI compatible interface, which means that you could develop your application internally just to query as if you were accessing the OpenAI ChatGPT, but you access your own open source LLM. And once you're ready, maybe for production, and you want to use the shiny ChatGPT 4, you can, and you don't need to change anything in your code, just the address. And on top of that, there is this amazing piece of technology called LlamaFile, which has been created by in partnership with Mozilla. And what it does is it takes this llama.cpp runtime. It will literally zip it with the weights of a model. So you have a pretty big file. Put on top of that a little bit of black magic. For people interested in this, it's called the Cosmopolitan libc. And what it does is basically you have one big file which is executable on Linux, Mac, Windows out of the box. Just a little caveat, I would make sure that you trust the source of this compiled executable because it can do whatever it wants on your machine. So on our case, we restrict ourselves to anything which is only published by Mozilla on Hugging Face to limit the risks. Okay, so once you have that, deployment becomes trivial. You download this llama file, you make it executable, chmod +x. If you're on the HPC and you want to access the GPU, make sure you load your CUDA modules and you run it in server mode. And voila, you have an LLM which is ready to answer your queries. Of course, that's only one piece of the puzzle, but in terms of deployments, I've rarely seen something as simple. And in terms of using a GPU versus a CPU, there's an interesting note to make here. For development purpose, so just if you want to see if the different pieces fit together and let's say my UI, is it responding correctly? And when I'm fetching data from the other server, is everything working? But I don't care specifically that the LLM does something good. You can use a tiny model which runs on a CPU super fast, like Tiny Llama. It's a great one. You give it data, it gives you garbage, but that's fine. It's just for development purpose. It's not to get something of good quality. And then once you're happy with it, you can switch to another model like Mixtral XX, so 8X7B Instruct. It's quite a nice one. It fits into a 100 GPU with 40 gig of RAM. So that's quite a neat one to use. Okay, then next come our data input, as I mentioned earlier. Then for that, we'll connect to two different servers, and one is called a thread server, thread data server. And this is where internally at NIWA, we have some of the forecast data saved as netcdf, but in that case, we don't really care about the netcdf aspect of it. We just need to make a little HTTP query with the time we want and latitude, longitude of the location, and it returns a CSV. Trust me, it's almost 3 to 5 lines of Python code, and so it's quite easy to request data that way. And similarly for the observational data, so weather station data, if you want to include a bit of context, we can connect to the ClideDB database, and it's a SQL request. Nothing out of the standards here. Okay, so comes the prompt generation. So, okay, how do we merge this data? How do we make sure that everything gets together and we feed it to the LLM? As I mentioned earlier, if you're using the OpenAI or llama.cpp servers, the interaction with this model is actually very basic HTTP API, and basic, I mean it in a very positive way. It's literally few lines of code. It's not hard, which means that I was wondering at the beginning, okay, should I use LangChain or any of these shiny LLM frameworks? And there's probably one popping every week. And the other was like, maybe no. And I'm really happy I found this blog article from a person I absolutely don't know, but that was sort of mirroring a bit my feeling, which was like, okay, you can achieve a lot by just, using your usual text processing tool, because at the end of the day, we're only from the engineering side of things, we're only merging and moving text together, which means that, woohoo, the amazing toolbox I used was the dot format methods from Python strings. And it's enough. It's just enough. So yeah, not today. I won't be using LangChain yet. Just as an illustration, it means that when it comes to sending the data to the LLM, so the prompt, it means I convert the numerical data to text, I inject that into placeholders left in the prompt, as you can see on the right with these curly braces. I use this dot format method, and that's it. That's all you need. Nothing more complicated than that. One little thing to know is, especially if you're using open source LLMs, is each of them has been trained with a slightly different prompt template. So they have a sort of tokens that they put before and after the actual wording of your request. And you need to make sure that you take that into account. So that's why here you can see the Llama 3 prompt template as an example. Okay, next, the cherry on the top, or maybe the icing on the cake. Yes, you can tell that the tea break is soon. The Streamlit dashboard. So that one has been built with a Python package called Streamlit, which is very good at making these nice interactive web interfaces. A good thing about this one is the way to write a dashboard is very much like an imperative script, and it does a bit of caching under the hood to hide the complexity. You don't have too many callbacks to use there, or even none. If what you're trying to do is simple enough. Has many nice widgets out of the box, a good look. It supports data frames, good integration with plotting libraries like Altair, which I do recommend for interactive plots. And for prototypes, I have to say it's very good. I can't say if that will scale, but this is for internal experimentations. So yeah, we don't really need something bigger. And on the right here, you can see what I was meaning by this imperative script style. You have the different widgets which are created, and it will literally evaluate from top to bottom, and if the button has been pressed, it will go to that branch and execute that part of the code. And so now, just to conclude a little bit on this, probably a bit fast tour of this system, the key message I want you to take away from this talk is you can get started nowadays with open source LLM. They are great. You don't need a GPU to develop. You can even use CPUs to do some decent inference. You don't need an OpenAI account. You can get started on your friendly HPC system or even your beefy machine at home. And for us, the Llama file plus Streamlit plus the format was a good combination. I'm a happy dev. I have a simple stack to deal with, and I have happy users. On that note, tēnā koutou, tēnā koutou, tēnā tātou katoa.
Awesome. Thanks, Maxime. Right, we do have a question for you from Paula. Actually, more coming in now. Classic. So from Paula first. How do you measure usage for reporting and or improvement?
Sorry, can you repeat the question?
How do you measure usage for reporting or improvement?
Yeah. So at the moment, we're talking about a small crowd of 4 to 5 people. So we have just informal meetings where we evaluate how things are going, and it's an iterative development process. So usually you add a little widget, rename things. And as I mentioned briefly, there is an experiment tracking. So we have a little database, a SQLite database, and we can use that to actually see when people have been accessing the tool and using it, and we track everything.
Awesome. All that data, so valuable. Right, next question, Maxime. You're not off the hook yet. Any suggestions on how, this is from Alex, any suggestions on how to mitigate hallucination? Are you giving a prediction that is only partially based on the supplied data?
So I don't have a lot of things to say about that topic, because again, here the idea was mostly to provide a tool and put it in the hands of the practitioners. So sadly I don't really have a good recommendation for that use case.
All good. Maybe that's the next phase. And from Olivia, thanks, Maxime. Have you ever tried Shiny for Python? And if so, do you have comments about Shiny versus Streamlit?
No, but sadly, I mean, I've been trying a couple of things, but I can't recommend pro or against Shiny for Python. It looks like an amazing tool on the surface. Again, Streamlit, not sure the pronunciation, did the job for us, and I do enjoy using it. Doesn't mean the other tool is not great too. as you've seen before, there's quite amazing things you can do with it. So I would suggest at least to give a try to both, and maybe there is one paradigm that will click a bit better with you.
Awesome. Very diplomatic answer there, Maxime. Oh, another one in from Benedict. Thanks, Maxime. Really cool talk. In your opinion, how well does the chatbot perform at summarizing the forecast?
That's not an information I can disclose. Yep.
Sorry, Benedict. All right. Okay. I think you're off the hook now, Maxime. Fabulous to hear about that work. Lots of really interested people. All right. So we're at the end of the final session for the day. So first I get to thank Chris and Maxime again for sharing the work that they've done with different researchers to support that research. Thank you to everyone for participating today. I think we had 39 of you all at different times through the day. It's great to have that turnout to be focusing on research software in New Zealand. We don't get to talk about it enough, right? I have two notes for you from the experts behind the scenes. First one is that the welcome and keynote recordings are already available for you to have a look at on the platform. So if you missed anything from this morning, from that keynote session, you can go and watch it this evening with a cup of tea tomorrow before we start at a luxurious 9:30. So tomorrow morning, the program starts at 9:30 and we'll kick off with a keynote from Dr. Erin Kwan, a researcher from the Mātai Research Institute. So that's all for today, folks. Enjoy another little bit of time to get on top of the things you've missed while you've been talking research software today, and we will see you ready for more engagement tomorrow. Thanks, everyone.